sure that this data is clean enough and diverse enough in order to provide it to the machine, so we can actually apply algorithms in order to know, for example, if we are trying to do a classification task, we have for you a lots of images for this object, and see many of them in different conditions, in different articulations, so that when we give you a new image at the end, the computer will be able to identify that this is similar to what it has learned before. Okay, so why this task seems really very, very hard? So if we take an object like a cat, as you guys know that this cat could be having a lot of articulation here. This cat is very, very flexible, as you can see. So it has so many ways that it can show to us as a human that we can easily recognize, but this kind of articulation or occlusion, like part of the cat is hidden, or this kind of fancy looking cats, as you can see, a lot of variation that we need to introduce to our algorithm or our computer, so it can capture all of this variation, and later on when it sees any new image like this or any other, it can know and understand that this content is similar to what it learns before. All right, so this is like briefly the goal of computer vision, or in particular now I'm going to zoom into a particular task, which is a classification task. And nowadays you guys know that we have so many sources of information for images and videos, Facebook, Twitter, WhatsApp, we have so many of them. So we have tons of data. So now how can we actually use this data for any task like classification, recognition, detection, segmentation? I heard a lot of you during today's session. I joined early, actually, like 8 my time, which is 5 your time. So I heard all of you, such amazing work. But again, and now I'm going to zoom into a particular task, which is my first entry to the computer vision domain, which is the classification. So in order to do a classification in particular, there is a very standard technique, which is called the bag of words. And this technique actually was borrowed from the text domain, the text classification. So when I started doing this research, I was fascinated about how can we translate a knowledge from one domain to another. And it became now, after I started in 2007 and now to 2020, it became like a second nature for me now to know that learning more from other domains that is advancing is very, very important to actually leverage their advance and then figure out a way that you can actually merge the fields together. And this is one of the most important things that I have learned throughout my research so far. And again, so I will go over what do we mean by the bag of words in computer vision, and what is the limitation of the approach, because when we learn about an approach, we need to know exactly what is the drawback, so we can start actually tuning or figuring out ways of fixing the problem. So lots of research happened to address this, this limitation by introducing the spatial information, which is called a spatial pyramid. And again, it has some kind of drawbacks that I will touch on them today. So I will let you know exactly what I have done in order to address some of these problems and do my research, and also how I applied all those new models that I was able to introduce or contribute to the computer vision to more of the application side. In particular, today, I would love to go over the agriculture domain. I think I don't have time to go over the satellite imagery, but again, all of the work is published in an open source. If you go to the Robotic and Vision Lab at the School of Electrical Engineering, you will see all the PDFs of my publication open for free to everyone. So again, what does it mean, the bag of words? As I mentioned, if we would like to teach a computer any class or any category, we need to collect images. So we have to start by a data set, a big data set, a clean, diverse enough so that it can learn from this knowledge or this information. And then we use these images and try to figure out a way that we can actually extract important information. So for example, if we are trying to do face recognition, so we will collect lots of images for humans, and we will look at eyebrows as a feature, different noses, cheeks, chins, and then these are the features that describe or discriminate one person from another. So we collect these features from every image that we have, and then we try to bag them or group them or cluster them into what we call the bag of features. And then we try after that to go into each image and we describe it using a histogram, and every image is now quantized by what's called the histogram of the important features. Then we give this new description of each image to statistical methods such as the support vector machine, so it can learn a lot of this diversity, a lot of this differences between the images, a lot of difference in the colors between the images, and it builds a statistical model so that when we have a new test image for a new human, and then we try to calculate or represent it using the same way, which is a histogram of the features that we collected from the bag of words, and then we pass it to our model, it will give us a probability that this image is a person or not. And let's say if the image is a face with 90%, we will trust that this image is a face, not a car, for example. So this is briefly the bag of word, which is a standard technique in classification. But as I mentioned, when we have a face like this, the bag of feature will collect the important features such as the eyes and the chin and the nose. But as you can see here, it puts them in a bag, which means that the local information is completely ignored, or the spatial information. So that's why we need to make sure that we always keep track that the eyes, for example, are always on the upper part of the face, and then the nose is in the middle, the mouth is on the lower part of the face. So this kind of spatial information will be very, very useful and make the model much more precise and accurate at the end. So that's why people come up with this spatial pyramid, which they actually describe the image using histograms, but they divide this image into like quadratics. So they divide they have the initial image described by, let's say if we have a vocabulary of 1,000 word, visual word. So they describe the first image as is without information spatially considered, and then they divide the image into 4 parts, and then they describe what is the features here, how many times the eyes happen on the top left corner, and then how many times, for example, the eye happened on the bottom left corner. As you can see, we should actually find 0 here. How many times the eyes happened on the top right corner, how many times the eye happened, for example, in the top left corner, the bottom right corner. So by having this kind of spatial information, we can preserve the location information, which is very important, and it actually proved to boost the performance of recognition systems very, very much. And the more we go deeper and deeper in doing this kind of subdivision, so if we take any square and then we divide it again into quadratics, this will have or lead to more accurate representation. But not every time we only want to look at the accuracy. We also need to make sure that this representation is not computationally expensive, because so many applications cared about not only the accuracy, but also very sensitive to the computation complexity. And that's actually one of the main shortcomings that I have noticed when I started my research, and I started to figure out, okay, is there a way that I can keep, or we can keep the content of the spatial information without this kind of huge computational information that is a shortcoming? This is what I will show you how I address this. Second is that why this kind of this rigid representation is the best. So for example, if you can see here, the airplane on the top left corner. So we only have the information at this part, or if we have a crowd of people. So the information people will always be on the bottom part. So not all of the subdivisions will be the best. So is there a way that we can actually preserve the spatial information in a more realistic way, or in a more flexible way that it actually capture the scenes or the context of the content of information in a smart way. So these are my first contribution to the Society of Computer Vision, is that I was trying to, first of all, figure out a way to reduce the complexity of the spatial pyramid so that we have a compact yet discriminative representation of this bag of words that preserves the spatial information. And once we obtain this, we can actually leverage lots of other complementary information. So instead of only building a spatial pyramid that takes into account the shape features, for example, that came from the HAR or the hug or the SIFT, why don't we actually take into consideration other important features like color information or like texture information? Now we have this compact spatial information that preserves the same accuracy as the original one. So why don't we actually now complement this representation with other features, because we have now the luxury of the small representation. So that was another thing that I introduced after I was able to propose the compact spatial pyramid, that now if we were able to do this, and this was accomplished, then how can we actually make use of combining useful feature by leveraging this compact representation? So what I did in this is that I said, okay, looks like if we take 2 levels of the spatial pyramid, there might be redundant information. What can we do to do this? So let's assume that I have a vocabulary of 5 words to describe a face. Let's say eyebrows, eyes, nose, ears, and mouth, for example. And for every face, I count how many times I have seen those. So I build a histogram. And then again, for the second level of the spatial pyramid, we have 4 squares. So every square is represented by a histogram of the same size. So my way is that if I can make use of an algorithm that was proved to capture any redundancy of the information, and I was able to maintain the same accuracy with smaller dimensionality reduction, this is a win situation. So I looked at the information theory literature. Again, this is what I told you in the beginning, that learning from other domains that actually advanced, and at that time computer vision was still not very advanced like this moment that we're talking about. So I looked at the literature and I found that there are so many useful algorithms, such as the agglomerative information bottleneck theory. This is a bottom-up approach that measures how redundant or how useful are the content of information. And also I looked at what's called the divisive information theoretic clustering. This is a top-down approach. I also looked at the principal component analysis that every one of us learned in the introduction to computer vision, the partial least square. So, and then I tried to benchmark my results. For example, if I start with a vocabulary of 1,000, then I will end up with having normally a spatial pyramid of a size 5,000. This is actually very small, but let's now see it for simplicity. If I was able to reduce it to 500 or even 50, maintaining the same accuracy that I have, so this is amazing, right? So I did this experiment. Actually, I took 2 data sets. I start with scene recognition, and then I try to apply the compression using all of this information reduction techniques, the DIDTC, the PCA, and the partial least square. So I try to compress it as least as I can, and in the vertical part, you can see this is the precision, how much of the information or the accuracy of my classifier is still maintained. And as you can see here, some algorithms like the divisive information theoretic clustering was able to maintain very high precision with very low vocabulary. So this was my contribution, my first contribution to the society, which is published in the Pattern Recognition Journal in 2011. So this is when I said, okay, I love this field and it's rewarding and contributing, let's move forward. Okay, so next I said, okay, that was my first goal. My second goal is like, okay, now I was able to not only use the spatial information, I reduced it. Now I wanted to make sure that my system can make use of complementary information. So I used SIFT before, which capture a lot of like shape information, now I was looking at other cues, like the color cues and the texture cues. So a lot of literature at that moment was actually making use of the color information and the SIFT and the HOG at that time. But I found that texture information, especially at that time I was working on scene recognition, is very, very useful, but not so many people was actually addressing this problem. So I started my work by looking at the textual descriptors. And I, again, care about not only high accuracy, but also I care always about the computational complexity. So I'm not sure if you guys learned about the local binary pattern textual descriptor, but this is actually very simple to compute, but it was new. So I was thinking that, okay, how about that I try to leverage this information, which is a textual information, and combine it with the shape and the color information and see how this will impact the accuracy of the scene recognition tasks. And now I'm leveraging again the low, the compact spatial information. And we have been achieving like the state-of-the-art results at that time with this new pyramid of local binary pattern, which is computationally less expensive as this compact. Again, we always benchmark our results, our contribution with the state-of-the-art texture descriptor, which is like Gibber, which is the local binary pattern as itself without the spatial pyramid, the local binary pattern with a spatial pyramid that I introduced, which is dimensionally reduced, in addition to color information such as HSV or the opponent color space. And again, we also was able to, as you can see in our standard database comparison here, that we exceeded the state of the art with also lower computational complexity. And this work was published in another journal, which is my image and vision computing journal in 2012. So the third question that I started with at the beginning was like, okay, now let's look at the third problem. Why we always need to stick with this rigid representation for every particular object of interest, especially if I'm looking at the scenes. For example, if I have a scene like this, I have a beach, I know that on the top there's always a sky, on the middle there's always water, and then there's always sand. So I don't need this kind of 16 divisions to capture important information. I think this was my assumption, that probably 3 is enough, because I know that the 3 sections 1, 2, and 3 are different. And if I was able to describe the content of information using color or text or whatever is going to be useful in this case, then that's going to be an advance. And this is what I did. I again relied on the algorithms, the agglomerative information bottleneck theory. This is the information bottleneck theory. This is not my contribution. My contribution is how to apply this new this information theory principles that it actually groups or removes redundant information and brings to me the important division that's needed for each category. So I merge the information theory with the computer vision so that I can learn the best content description, the best spatial description for each category. As you can see here, I tested this on, again, scene recognition classes. One of them was, as you can see here, the beach, and I was able to, as you can see here in the lower part, this is the initial starting point. The algorithm is trying to incrementally merge the cells. So like here, this is 3 and 6 was merged together because it looks like the information here is redundant. So that suggests that this division was not useful. In the second step, 1 and 4 was merged. And then at the end, we find out every time we measure, we have a new shape or a new spatial representation, we measure the accuracy. And then until we find or we test, what if we didn't divide at all? Is this actually the right thing to do? And then the spatial representation for each category that maintains the original information with the minimum complexity is the one that we actually keep in our training phase. And as you can see, the results actually make sense with our hypothesis that for this scene, we were able, using the AIV or any information theory, but in my case, I use the agglomerative information bottleneck theory, to prove that the rigid shape is not the best in this case. actually the hypothesis was true, and it described the information in a more accurate way in a less computation. I tested this on many other classes like forests, like open country, like highways, like tall buildings, and we were also fascinated. And again, this was published in the Image and Vision Computing Journal in 2012. Okay, I then move forward about, okay, all of that was scenes, how about objects? So if you guys, I don't know, there is a very popular competition in computer vision. It's called the Pascal Challenge. So the Pascal Challenge in that time is introduced when I was in Spain to us. And people were asking, how about we, in my lab, we contribute, that was the first year, I think, or the second year, we contribute using your algorithm and other colleagues' algorithms and just try on this. But this is an object recognition challenge. And this year, I recall that we got the second place internationally. And we applied, this was one of the algorithms that we actually used, is that we tried to compress our representation, merge many cues, and smarterly learn the right subdivision for each category. So at this point, I will just move to, I end my PhD, and then I moved forward to Amsterdam to learn about what is the impact of color constancy in increasing the accuracy of the model. As you know, when you take a picture with a camera indoor, it will be very different from outdoor. So how we can tell the computer that there are differences, and how we can quantify these differences so we can correct for this. Because this is another project that I have been working on. I published my work on the transaction of image processing, and it was also very useful. But I'm not gonna go over that today in the sake of time, but I would love to tell you my first project I did once I joined the Purdue, the Robotics and Vision Lab, in particular the agriculture project with the collaboration of the United States Department of Agriculture and University of Pennsylvania. So we published a lot of work. Again, all of this work, you can see it from the Robotics Vision Lab. It is published and it is posted there. So we had this challenge. So we started that they came to us and they said, look, we would like to collaborate with you. So you are a vision and robotics lab, because we have this project every year and we wanted you to assist us. So we have this dormant pruning. So in apple orchards, they usually, in particular, prune the trees in the winter in a certain way so that they can actually make sure that the trees are healthy and the production is increasing year after year. But it has to happen in the winter, which means that they need to only have or rely on workers on a particular season. And these workers usually are immigrant. So there is no guarantee that they actually can have the workers, and these workers might not be even skilled or trained enough, so they have to train the workers. Or as you can see now with the COVID-19, they might not be able to have these workers. So there is a lot of risk and uncertainty. So they said, if we are able to automate this process somehow, that we can assist the workers, not replace them, because they were actually scared in the beginning to do this with us, not to assess the workers in case of any emergency, or we couldn't make the numbers to bring enough workers, or we couldn't train them. So that would be great. Can you assist with this operation? I said, okay, let's try. Looks like a very challenging problem. So again, our goal was, first of all, is to go to orchards, do data collection. So we did this in Indiana, and we also did this in Pennsylvania, because there are plenty of apple orchards there, apple trees. And we had to do this data collection in the winter, because the pruning has to happen in the winter. So first of all, always in any research, is a data collection. And once we had our data collection, then we try to figure out how can we represent this data using computer vision. So we use sensor to collect the data. We started by using the LiDAR, which is actually very big, very heavy, very expensive. And then we explored other techniques, such as the Kinect that we use actually for gaming. Is this a venue for sensing the data? Yes, we know that the accuracy will not be as good as the LiDAR, but this is also mobile. This is less expensive. That's more practical. And at the end goal, we would like to make robots use it. So it's going to be easy to integrate it with a robot arm. So we tested plenty of sensors, and every trial of success and failure, we publish it so that we actually disseminate the knowledge with the community. And second goal is that once we collected the data using various sensors, and at the end we actually landed as a Kinect because of the ease of handling it and the lower price and so on. What is the model ways? Because remember, computer only know numbers. How can we translate the trunk and the branches into numbers? So what is the algorithm that we can use to build 3D models so we can actually identify the points to the computer and the robot in the future that they can actually prune it? And then finally, how can we assess that these points are actually accurate? So we needed to create a visualization tool so that it can actually show us all the metrics, all the points in a nice way, so we can actually verify our data. So as I mentioned, I will just go quickly over my slides. We investigated the use of many sensors like laser scanners, LiDARs, Kinect, and this is me and my students collecting data in very, very, very cold weather. You don't know how cold it is. And then again, doing using the domain expert people from agriculture who tell us in real life in what do they do, what are the right points, so that when we apply our models, we know exactly what is the ground truth, how can we assess. We use this color coding to know exactly where the robot should go, where the model should know. And then we went, again, so this is the citation of the work that we published in CVPR 2016. And then once we collect our data and use the domain knowledge to know exactly what is the ground truth so that we can train and build our models, then we try to actually use computer vision. So this is the computer vision part. So we tried first to detect the trunk. So we applied many algorithms. Is this better to use circular-based modeling or cylinders or arcs? So we tried many of them. And again, we applied the same models on the branches, the primary branches and the secondary branches as well. And then we tried after that to quantify the tree using numbers, because again, computers only knows numbers. So at the end, using the circular model, for example, we said that every branch is identified by a branch ID, has an index, a branch radius, and every primary branch which comes from the trunk should be described again by an index, by a radius, and by the angle, how it is tilted from the trunk, and also the ratio, how thick is this primary branch from the trunk. And we actually get this information because this is what people do in real life, in their daily life, to judge which branch to be cut and how much and where exactly. So we get this information, we learn a lot from them, we verified a lot with them, we do a lot of prototyping so that we make sure that our model is what they are expecting and it's going to work in the future. Again, this work was published after we compared several models, 3D models, in the Journal of Field Robotics. Afterwards, we actually, once we created the model, compared various 3D models, we wanted to validate our model. So again, this was a time that we really want to see, and we wanted to show them as well so they can actually see. They don't understand 3D models, our end users, right? So we needed to make sure that all of these numbers is actually shown somehow. So it is very important to visualize our data. So we built a graphical user interface where we actually show the tree for them, and the tree is actually rotated like 360, and we show them all the information, and we even show them if we apply the rules, because we captured all the rules. If we, for example, prune all the branches which are within 60 degrees, and what's going to be the impact on the health of the tree, and we also get all this information from them. So we were able to generate this nice multifunctional graphical user interface that can show to them the tree and the impact of pruning or not pruning, and what is the state of the tree at the end here, so that we can actually get quick response about is this right? We are right. Is this what you are expecting? And also later they ask us that they use this for training their farmers, or when we publish this in conferences, they ask us to share it with professors who are teaching this in school to educate the students in agriculture about how to use technology in educating the students about the pruning and things like this. I'm not sure about the time, but I think I might stop here at least to see if there are questions or if I'm moving very fast. Let me know. Hello guys.
هاي دكتورة نوح خلصتي؟
I'm finished the part with agriculture. I'm not going to be over time. I'm already over time. But if you guys have any questions, I would be very happy to take them.
Yeah, regarding the agricultural project that you have participating, what about the, you know, some plant images or some plant recognition and disease diagnosis? Are you working at this point or not? In your project, or are you planning to work on this point? Because as I know, for plant diseases, there are many problems and the challenges.
Yes.
You know, feature extraction, for example, to propose a new feature, we have to take into account whether it is easy or not. For example, with the climate change and the climate change, the shape of the color can be changed. This is one of the many challenges here. Also, you have the image capture conditions, and you were talking about it. The condition of capturing images usually uncontrolled, which can cause difficulty in prediction or in the characteristics of such images. Also, in practice, images have to be captured at the same or in the same conditions. What will you do with these challenges?
Actually, that's a great question, Dr. Ashraf. With this project, we have been learning all the time, and we have been exposed to so many. Oh no, we learn a lot of fundamentals in computer vision, but I have not seen how much of them can be put together in one project like this. So so this kind of like the infected diseases or things like this, I think we should actually try to think about new features. This is still an ongoing work. There is a lot to do. And again, if there's any students that you know are willing to do.
Yeah, it's an important challenge for your project, I think.
Yeah, and it is even here in the US, not so many labs are working on. And is that, as you can see, it is like an end-to-end. So we started with the data collection. We started with the 3D modeling. We know now that we have to do a perfect data visualization. We know that we have to go to do simulation before robotics. But also an important thing is that we need to make sure that our features that we collect is the right feature. So far, because in this project, we have to deal with the trees, which is without leaves, leafless, because this is when we prune it, it has to be like this. We did not deal with the leaves. But let me share with you something else. Maybe here, if you can see my screen. I didn't go over that. So the other project that we work with, which is query localization. This is a project that we collaborated with University of North Carolina and the Applied Research Association, and we have a fund of 40 million. So what is the goal of this project? They give us like an image or a video, and they said us, can you tell us where this image was taken? And this was very, very hard. And they only give us a satellite imagery. Okay, so we said that we will try, but we said that what we can do is that we can look at landmarks. One of them is actually the linear trees. And in order to detect the linear trees or the crosswalks, we have to come up with the new features. So when we were dealing with the linear trees to be detected, we come up with our own features. We did what's called the land cover classification, and we had to use a lot of physics and Fourier transforms to learn a lot of information about the trees, and the description of the trees and the texture information was very important here. So, but we learned from this project that we always need to create or come up with features that best suit the problem. And so in this case, if we have a project that deals with grasses or trees that have leaves, or we need to detect the infection or learn more about the leaves, we have to define our own features. And we did this in other projects, and this is an ongoing work, I think, which is very interesting, and we'll be very happy to collaborate if you have students that are interested or if you are interested.
I can add that we have another challenges with planted images that the symptoms of the diseases are very similar. So in some cases of diseases, the symptoms of images don't have defined ages, sorry, or boundaries, which make it difficult to identify. It is important in this case to notice that any change in the boundaries of the region of interest may impact on the extracted features to describe this region, for example. I think with plant disease, I think we have many challenges, many problems that can be solved in the future. I have a question from one of our audience here. He is asking Dr. Noha, how can you trace the image of plants during their growth?
Okay, thank you, Karim. I haven't worked on that, but I know that some of my colleagues at Purdue was working closely with faculty from the agriculture in order to address this problem. And I think that the first thing that they do is that they build a lot of simulators in order to figure out. And I remember that some of them like they mounted some images and some cameras in order to collect a lot of information through different seasons in order to collect a lot of information so that they can start working on that. So this work has to be, like, based on my experience, has to be in close collaboration, not only from computer science or computer vision, but also from people who have an expertise in agriculture, because we really complement, we verify every information with them, really like babies. Every step that we do, we have to show it to them. That's why we built the graphical user interface, because we want their guidance throughout our ways. And with their feedbacks, which was very useful for us, we always refine and learn and then give them a feedback. So this is a very collaborative work which has to be done with the domain experts, in this case, faculty members from agriculture.
I agree with you. Yeah, what we are doing here, we are trying to find another way to help some experts in agriculture, not using the traditional methods to identify or to recognize some plant images or something like that, but we are trying to help them. Anyway, the time, I think it's over now. Just a moment, may we have another question? They thank you very much for amazing, they are writing that amazing and wonderful presentation and for the information in this presentation. I personally, on behalf of Professor Abu Al-Ala Hassanin, the chair of the conference, and on behalf of the organizing committee, Dr. Professor Shireen, Professor Sali, Professor Ahmed Al-Siddawi, Dr. Muhammad Abdel Fattah, Dr. Murad Rafat, Dr. Mahmoud Shams, I would like to thank you so much for this wonderful talk, and we hope to see you, inshallah, in the next conferences with us. Thank you so much, Dr. Noha.
Thank you so much,
hope
everyone.
to be in contact with you. Thank you.
Thank you so much. And I also posted my email. Feel free to connect by LinkedIn or email. I'll be very happy to collaborate. Have a wonderful day.
Please.
Thank you.
Thank you. Bye-bye. Have a nice day. Okay. Dr. Azza? Dr. Azza?